Op-amps are much more than just amplifiers. You can also use them for debouncing buttons, building flip-flops, electronic fuses, oscillators, and even an optical sound system with a laser. Curious how that works? Then watch until the end. The simplest op-amp circuit is definitely the comparator. If the voltage at the positive input is higher than at the negative input, the output jumps to its maximum. Otherwise it drops to the minimum. Both are near the positive and negative supply voltages. If we add two resistors to this circuit, we get a hysteresis. That means the comparator switches on at a higher input level than it switches off. So we've essentially created a Schmitt-Trigger. The ratio of the two resistances multiplied with the maximum output voltage determines the width of the hysteresis. For example, if R1 is 100 kiloohms, R2 is 20 kiloohms, and the maximum output voltage is 5 volts, the hysteresis is 1 volt. Here's the circuit set up on a breadboard. I'm connecting a function generator and two oscilloscope channels, so I can easily compare the input and the output signals. In XY mode, the oscilloscope clearly shows two thresholds. After placing the cursor on them, we can directly read the voltage difference. It's 1 volt, just as expected. With the trim port I can change the reference voltage and so change their position. Here's a blinker circuit with a 555 timer IC that drives a relay. On the oscilloscope we can see the voltage switching on and off. But when we zoom in, you'll notice the contacts bounce quite a bit. This is where the Schmitt-Trigger really comes in handy. A small 33 nanofarad capacitor damps the glitches, and the Schmitt-Trigger gives us clean, crisp transitions at the output. Here's another version of a Schmitt-Trigger circuit. Unlike the one we looked at earlier, this one inverts the input signal, as you can see. By adding two diodes and two more resistors, we can build an RS flip-flop. If you want to really understand how this works, watch the voltages at the op-amp's inputs. When not driven high, the inputs must remain floating. So the diodes prevent it from being pulled to ground if the previous stage outputs a low level. But depending on the circuit, you can also leave them out. Here's a use case. An electronic fuse circuit. The output of the Schmitt-Trigger controls a MOSFET that switches a load. At the MOSFET source, there's a shunt resistor. The more current flows through the MOSFET, the more the voltage drops across this resistor. That voltage is sent through a voltage divider to the inverting input of the first op-amp. At the non-inverting input we have a potentiometer to set a reference voltage. If I switch on the second bulb, the current gets too high. So the voltage at the inverting input drops below the reference, and the op-amp sets the RS flip-flop. The output then goes high and turns off the MOSFET. Pressing the reset button resets the flip-flop, turning the fuse back on. The proof that this circuit works is this test setup. When powered on, the flip-flop starts with its output high. That means the P-channel MOSFET is off. So I need to reset it first using the reset button. But with a 1 microfarad capacitor in parallel to the button, the flip-flop will always start in the reset state. If you want a more solid and professional way to build this circuit instead of using a solderless breadboard, check out the sponsor of this video, PCBWay. Instead of assembling your circuits on messy breadboards, simply send them your Gerber files directly from KiCad via their plugin, specify your requirements, and a few days later the boards will arrive. I love the high quality PCBs, and that's why I love to work with PCBWay. Soldering is always fun and done in no time, even for beginners. And PCBWay not only makes PCBs, they do also offer CNC machining, sheet metal works, 3D printing and injection molding. Get everything you need for your awesome projects from one hand, so give them a try. Now back to the topic. With just a few components we can build an oscillator circuit. Using the potentiometer, we once again create an inverting Schmitt-Trigger. A resistor connected to its output charges a capacitor. This causes the voltage at the inverting input to rise above the other threshold voltage at the non-inverting input. When that happens, the output goes low and discharges the capacitor until its voltage drops below the lower threshold value at the non-inverting input. At this point, the output goes high again, the capacitor charges up once more, and the whole cycle repeats. By adjusting the potentiometer, we can widen or narrow the hysteresis, which lets us change the frequency across a broad range. By adding another potentiometer and two diodes into the feedback path, we can control how quickly the capacitor charges and how fast it discharges. This allows us to adjust the duty cycle. We can build a triangle wave oscillator by combining a Schmitt-Trigger with an integrator. You might remember from school that integration in mathematics means calculating the area under a curve. So if we integrate a positive constant, we get a rising ramp. If we integrate a negative constant, we get a falling ramp. Here, however, we have an inverting integrator. That means a positive input voltage causes a falling ramp, while a negative input voltage causes a rising ramp. So if the output of an inverting integrator is fed back into the Schmitt-Trigger toggles its output whenever the upper or lower threshold is reached. This results in a square wave at the Schmitt-Trigger output and, consequently, a triangle wave at the output of the integrator. If we feed this into another op-amp that's configured as a comparator, we get a rectangle wave whose duty cycle can be adjusted by changing the reference voltage. In other words, this gives us a pulse width modulation. PWM is extremely versatile. For example, it's used to control the speed of DC motors, dim LEDs, synthesize musical instruments, and even transmit signals in the AM band. So check out these videos. Here I've connected a laser diode from an old laser pointer to the output of my PWM circuit. Its beam is aimed at a photodiode which acts as a receiver. While the simulation tool doesn't include a symbol for a photodiode, I can model the optical link using a voltage-controlled current source. Now the first op-amp works as a transconductance amplifier, which converts the photodiode's microamp level photocurrent into a voltage representing the PWM signal from the laser diode. With the potentiometer, we can adjust the amplification to match the intensity of the incoming laser beam. PWM is easy to decode with a low-pass filter, so the other op-amp is configured as such. And at its output, we get the original signal. And if you'd like to try this circuit yourself, feel free to pause the video here and take a screenshot. And because you've made it this far, don't forget to like the video, subscribe to the channel and ring the bell so you won't miss any of my future experiments and deep dives into electronics. And of course, I don't want to just talk about it. I want to show you this in action. I've connected a phone as a music player to the PWM transmitter and added an LM386 audio amplifier to the receiver circuit so the music plays through a speaker. The amplification for the receiver diode needs to be fine-tuned until the sound quality is at its best with minimal distortion, but still enough volume. Of course, this also works with a powerful infrared LED like the one used in the Raspberry Pi camera modules. It's connected here to a simple MOSFET driver. In fact, it sounds even better than the laser and doesn't require such precise alignment. But as a receiver diode, it's better to use one designed for infrared. These have a built-in blocking filter for visible light, which makes them insensitive to ambient lighting conditions. That's all about it for now. Thank you for watching, see you next time.